Okay, so this lecture we're looking at the shaders and going to complete all the shader coding. Uh, well, the one reason I'm talking about buffers, there's a connection that has to make clear what is the flow of the graphic pipeline and how does that work. So I believe this lecture and the follow on I might do both together and try to explain and finish the shader coding. Okay, so yeah, so let's start with the structure of the pipeline. um, there are a few things I want to point out here. We already know what is a vertex shader and what is the fragment shader. The vertex shader always take care of XYZ values, which is the position of all the vertices, and the fragment is always taking care of the coloring of it, right? So those are the colors. So one point that you are aware already is the connectivity pipeline. We first taking care of X, Y, and Z here, right? And that information is passing from the CPU side to the to the GPU vertex handling. So that is where the vertex shader is coming in, right? And then the vertex shader passing that to the rasterization. So this is where all the 3D image that you have in any shape, right? So you get the viewport and see what are the things that you see, not the back side, only the front side. So you map this to the 2D after this level. So it will be 2D from here, whatever the 3D data is getting from here. So this is what primitive assembly and rasterization means. You get the 3D data and you convert it to 2D. So this is where it's applying its coloring. So it's RGB values, right? And so the fragments means nothing but the pixels that going to take care of at this level right here, right? And yeah, so after when it reach this point right here, whatever we have XYZ values, and we are transferring all that to the rasterization, then you get a 2D image, and we are applying the 2D operations right here on this section, right? So this whole section right here is taking care of a 2D operations, okay? And then the raster operation means how are you going to draw that into the screen. So this is where the display comes in, right? So after you update your colors, you put that in the display, okay? Right, so here it is your CPU data, and you passing that to your vertex shader and handling that through the rasterization and coming into the RGB coloring setup, and then from there you just put it out to the screen. So that is the flow, the basic flow of how you take care of vertices and the colors or the fragments, right? So right, so let's move a little bit further here, and we should pipeline on how we really going to work with vertices and the data that we are handling here, right? So you can see in this one, these are just the vertices that you have, XYZ values, right? And then geometric operations, whatever you do, either you transfer these scale, rotate, whatever you do. So you can see now whatever the operations I have done here, now it has a different places for each of this, right? Yeah. So then this is what the transfer vertices means. So it will have some the structure in it. Then you assembly, process assembly means what are the shapes you want to draw with it, So these are the shapes that I have connectivity. So these are points, throwing a point into the system, and then I would say, okay, join these two guys, and then another triangle here, right? So this is a line and a triangle. So I have one line here and one triangle here, right? So that is what I'm processing. And then, okay, so these are the things which is you operate as a 3D. And now how are you going to point that in your pixel buffer or the pixel pack, right? So that is where you transfer this to the 2D, the raster or the screen, right? In here you will paint, okay, so this is actually diagonal line. So in that case, maybe you will paint these horizontal pixels, and then these ones, then it will you will see that as a line, right? This is what actually the pixel format of your triangle. So why we don't see it like this? Because the pixels are very small. If you magnify it, you can see it as a square representation here. But when it is very small, you don't see it. You don't see it that you can see it in out of shape like this, right? So then what you do, you apply colors. So this is where you are applying colors. So when you apply colors into the structure, so this is what you see. So this is the interpolation. That means the fragments you take in and you fill up with the colors, and this is the output look like, right? So this is the actual flow of a visual pipeline on a shader operation on anything, right? So this is, you need this process to follow up on any graphics interface that you see out there. Okay, right, so let's move to a little bit detailed pipeline here, right? So in this one, what I want to point out is that you're going to learn some buffer things. We already learned about PBO in one lecture, right? The PBO part is coming right here. Pixel unpacking and the pixel packing and the read pack pixels. This is unpack and this is pack, and this is the section we call the PBO section of it. Okay, and there's another one. I will do another lecture on frame buffers, which is called FBO, right, which is something that is falling into this area right here. This is called frame buffer operations or the frame buffer object. That is what comes here, right? All these comes with the fragment. So that means after rasterization actually. So pixel buffer also passing data into the fragment processing. So this is the rasterized data. Okay, so this is directly, if you are reading an image, it's directly go to the texture memory and then it will pass into here, right? So the texture memory also have to have unpack and the packing of the data of the PBO part, right? So the vertex operations from here to here, which is what we do in actually, yeah, up to here we do it as a VBO part, right? So we learn about VBOs, we learn about EBOs, right? All these we learn already, right? And VOA, VAOs, right? This is the vertex buffer objects. This is element buffer objects, and this is a vertex area objects. So we talk about these already, and all these passing the data into your geometry shader. And then after here, when the fragment processing going on, you have to apply some color packing. So the colors come into and join here in the fragment shader. And a few more things I have to talk about. After fragment shader, there is something called a frame buffer object, right? FBOs. And here also we have some other operations like for example The stencil is giving you more control on these things, so you can have more effects before you rendering it to the screen. So the stencil buffer comes here, and maybe if you have something with the shadow mapping, shadow stuff, you can do that here as well. So these operations yet to talk about, but this part we already covered, right? We will do some practical on that. So this is also, the soil handle most of these, the unpacking and packing the pixels. Well, there's not much to do with the PBO. It's just a buffer object that's passing all the pixel colors, right? So in that case you don't have to worry about that much, right? And okay, so the texture memory uh, is what we have RGB values, right? It's passing RGB values. And then we come to the frame buffer objects later on, and then we talk about that in another lecture, right? So this is the actual way of flowing things, right? So this is a fixed pipeline structure, and this explains the whole flow. So that is very important in the graphic flow to understand these things, right? So mostly in any language I think this will be the same. So the pixel groups are showing in the green here, right? And the vertex, which is XYZ values, this is RGBs, right? RGB values, right? And the other one is here, this is XYZ values, right? Again, these guys are RGBs, taking care of RGBs, right? In order to take care of RGBs, maybe you will handle XYZ to you have to pass these data from this guy to this guy to handle that. So the fragment part is very small in this case, but the pixel part have a substantial work to do, and the texture is just simply nothing but RGBs, right? So yeah, so this is the flow actually, the memory, how you get the data from memory, right? So so actually these things, even it's handling here, right, that has much direct connection with the memory. We are loading these things to the memory so you can share. So that's why this object comes into play. Okay, right, so let's see the next. Right, so fixed versus programmable. So I don't have much things to talk about here. The standard operation is a fixed function operation. That means earlier, before you come up with the programmable shader coding, not the shader coding generally that you're talking about, but the earlier days we did not have much control for the shader coding, right? So we just throw the colors and everything as is. You don't have to do yeah, like multiplying the vertices if you want, like cloning kind of things. We could not do those things. These days we have new shaders like geometry shader, right, and a few more others, or if you're using a CUDA as a GPU programming, so all that flexibility comes into play, right? So you can write and control most of the operations in the GPU these days. But earlier we did not have that facility, so that's why the fixed function pipeline comes in. It's a standard. You have to type of shader coding, the fragments and vertices, right? Vertex shader and the fragment shader, and then you have a little bit control, not that much, but most of it is standard fixed. And here we have more operational capabilities, so we can do a little bit more operations, right? So that is the good part nowadays. And yes, the pipeline processing has two stages. We already talking about this vertex and fragments, right? So okay, so what is the vertex shader actually doing? Vertex shader execute once for each vertex, so that means each vertex it will process So that's why it has that in the GPU you have a parallel processing ability, so you can pass each vertex into a one arithmetic logic unit and calculate things, and the other vertex or the other pixel, other point can handle by something else. So the vertex position transformation, usually using the model view projection. So this part right here is actually the rasterization at the end. So what you should see, what you should not see, and all that handling by vertex positions, right? For example, if you have something on the back side, you should not see it. On the front side, you see everything. So that part really handling by the vertex handling. And the normal transformations and the normalization means the XYZ values when you're having uh, the normal calculations. For example, if I have a triangle like this, and this is XYZ, this is X1, Y1, and Z1. So if I get 3 like that, of course I can have the cross product of this to get the normal, and then the normal is a huge value, so I can have this normal square it up and get the square root of it, right? And you divide your normal xn and the others, right? Yn and zn. Right. What this means is just divide individual values by this value right here, and you get the normalization, normal of everything, right? So handling that, and then also this guy has x and y, the texture coordinate generation, or ST and STU, right? Or either way, this is handling all the texture coordinates. Usually it's 2D, right? If you're using cube map, you have 3D. And lights per vertex means actually handling these values. It is nothing to do with RGB. It's mostly you are passing the normals and things like that. And this is what the same thing as a color computation, which is a shader part of it, right? But these two are just the XYZ part of it, not the RGB part of it. So the RGB values actually handling by the fragment. Only thing you can do is determine what is the normal values to pass into the fragment. So that's what it's meaning by these. So don't get confused with something else, right? Okay, right. So then when you're looking at the fragment processor, this is a fragment processor is for per pixel. So that means this guy, which is a fragment processor, actually handling everything on the screen. Even you have one object there. Let's say this is my object. Well, I can apply pixels to this one, separate from this one, right? So there are two different shader coding you can use here, or you can use one shader to take care of everything. The per pixel means if you're using a single shader, I'm talking about the resolution from here to here and the resolution from here to here, right? So that is if it is 1920 1080, we have something like that. So that means all the pixels with this. So that means per pixel means how many pixels are there is going to be equal to this much pixels that is going to take care. Right, so it's color everything. So you can handle things here. So that's why the stencil buffers and everything come into play and do some fancy things with it. We'll talk about that in another lecture, right? And the fragment shader executes for each fragment. Okay, so it is fragment means the per pixel shader. And then the computing colors and textures of, obviously if you have texture coordinates passing from your vertex vertex shader, right? That is XYZ values, and the normal values from there. So that is also XYZ. So using that to calculate the right color combinations, right? So this is what that part do here. Even the fog computation is inbuilt OpenGL feature that you can use the fog. I think they removed it on the recent OpenGLs, but it was there for some time. Yes, the lighting per pixel, right, depending on what angle your vertex is. So all these depending on these two values actually, and after you calculating things like here, right? Okay. So and also of one thing, if you have a texture coordinate values or the texture colors like RGB values, actually you can change these colors here. If I want to have R for everything, instead of G is replacing by R value and the B replacing by R value, you can do that here. Okay, so that is a funny thing that you can do actually, right? So like that you can apply to any object out there. You can simply calculate that with these kind of things. So that is a good idea. I was doing one research thinking of having an object and detect the boundary of this object or the 3D model in the direction that you see. Without detecting that, I can detect this in two ways. One is a boundary detection algorithm, or the other thing is apply this 3D model. So this is my 3D model, right, and it's trapped with some textures. So the texture color, I can say RGB replaced by everything by RRR. So in that case, I definitely know this object turned red, right? So that means whenever I want to detect the boundary, I can send a ray or just scanning this line, and if I hit this value, if I hit that value, I know that is a boundary. So I can detect this area right here pretty clear, and then also this one. Why? Because it's just a change, the clear change from this pixel to this pixel with the color. So if you identify this, obviously you can identify the boundary pretty easily. So that is one algorithm that you can use to determine the boundary of a view of 3D model, right? So whenever it's changed, this changed as well. So converting color into one and then process the algorithm will be easy way to do this, right? Right, so that's something. I don't know whether there's a publication for that. If it is not, feel free to do one. If I have free time, I would work on it. Well, we'll see. Right. Okay. So then how you write this? Well, I'm using a GLSL because that's the only thing is open supports OpenGL in this case. So we can use that. The GLSL is it is a C-like programming, and you have to compile it separate from your written program, and then you can link those to the OpenGL. Right, we talked about that already. We did some practical example in the labs. So what actually behind it is this, right? So the processing overview here, you create the program, you attach. So after you create the program, right, and then what you do is actually so this is what the process is. This is what OpenGL does when it is processing the rendering, right? But here is one part of it, which is you taking the file, which is a vertex shader, and you have a GL create shader, means you read this file and making a source available, right? So this whatever I have in my program, I'm reading it here, and then you do the compile process, right? So why? Well, because each of these programs here, you have some variables that you written up here, right? And then you have something called main, right? And then you have separate program. Here as well you have some variables, functions if you want, and then you have main. Inside the main you have this part right here, right? So so these two are there that you can use and then compile. So once you compile, it will create an object. So that is what we called shader, right? So you creating a program means you encapsulate these two programs, whatever you have, and I'm encapsulated into one. What is called, if I call create program A, so this is A, and then it's encapsulate that. And when you attach the code, means this is nothing but the compiled version of it. So you will have the compiled version of V and the compiled version of F, or the fragment. So those two will be in a one package now, and then you link that package to your program. What your program? Your program is your OpenGL program, right? And here you have main in that program as well, and then you do this part. So these two will be attached into this program by using a link, right? Use program means activating that. So whenever you have some object to print here and I want to activate this, I say use so GL use program, right? And then I'm calling here A, right? Once I call it A, this part right here will be belongs to this address by these vertex and the fragment shader. And then if I want to release it, if I have another object to print, I don't want to apply the same thing to that. In that, here you say GL use program 0. So it is here I say GL use program A, and then here I say GL use program 0. In that case, it will release this and then reset back. So otherwise, if I have more objects here, this same shader will apply to that. I don't want that, so I can break it, right? So that's how you're breaking it. So this is the process. How you code this, we'll look at in the next slide, next few slides. This is actually the process, okay? And to go more details on what this is the shader. Creating a shader is actually these are not directly OpenGL supported. You have to either use glue or new packages out there for the OpenGL. I think the advanced OpenGL these days with the GLM has embedded this, but early days it was not. So you're using a glue kind of a thing. The glut is not only supporting this, right? Yeah, we did that in the lab as well, so you know what I mean, right? So it's a create shader, and you get the shader shows source, and then you going to compile the source, and then you create the application out of that, right? Okay. And yeah, the process view, which is a shader handled by handler to the shader. So that is what I did here. We call create shader. So you to create a handler, and then so what is that process? This is what it's talking about here, handler shader. So you'll have a handler, right? So GL shader source, which means we have the handler right here, right? And then we have number of strings. So that means whenever you're reading this, it will read it into an array kind of a thing like this. So your file, whatever you written here, it will get line by line into this. Okay, so that's what it is, right? So number of strings means how many numbers, how many strings that you have. Usually I can combine everything when I'm reading to a 1 plus like what I can do is I can define a string shader, right? Or a shader like this, and then I say shader plus equals, and then each line I'm getting. So everything will be combined to a one string in that case. So I can have shader is a one string, so I can have one here if I want, right? And then Well, what is the name of the string? Probably this is talking about the shader, the name, and the length of it, obviously at the end, how much length of it, right? Right, so that is the pointer and all that come to play, and those are the parameters for GL shader source. So after you do this, you compile it, right? So that is the next step. Once you have it, you have to compile it, and then when you compile it, the program create the program, and so this is the interpolation part. After you compile it, you have to attach that. So this is where you're making the container, as I explained just a minute ago, and then this is where you're attaching all the shader and the vertex shaders to that program. And here after you attach those, you link the program and then using it, right? Okay, so look at the code on this. You can see it here very clearly. So I'm creating two handlers. These are one for the vertex shader, one for the fragment shader. And then you do is you say v, this v is not that, right? Okay. So this is the shader handler. Actually it's v is the shader handler, either it's an integer, I think it is an integer as I remember, and then create a vertex shader, and or you can call it, I think is the GL with the capital G L U int. That's what it is, V and F, right? As I recall, right? Right, so anyway, when you're having that, so I'm just saying, okay, well, I have one handler for vertex shader, have a one handler for the fragment shader, and then these two here are the strings, or the string of characters. I'm loading these values into that, so reading a file and load this into this, right? Once you've done that, you passing it to another variables. Why I'm using this, the constant vv equals vs and all this, because I can handle this. This is what I'm going to use for the rest of the program when I'm compiling it. So that's why I'm using that. Okay, right. And if I using a constant style at the beginning, I cannot update it. But now after you read everything into this, so that is only thing that you're going to use, right? And the shader source here, so we have a v as our handler, and the number of strings, it will be 1, right? And this is the pointer to my string, which is this guy right here. And the last parameter is the length. I just put null in that, so it will detect by its own, right, what is the length of the string, right? Or you can set up the string length here, right? Okay, and once you've done that, you don't need the vs and fs, so these guys you don't need anymore. So that's why I'm cutting it off. Okay, so it's very important, if you don't have the garbage collector like Java does, it's better that you just clear it up after you done with the process. Otherwise your memory will be piled up, right? So you don't need that here. Once you've done that part, the compile the shader v and compile the shader for f. So these are the handlers again right here, and these two guys comes here. And then you create a program. This is the container to handle these two, and then I'm attaching those values into that, right? So this is that, and then I'm linking that. So use program, you don't have to put it here. Once you rendering it on your display of your program, right, only in the display program in OpenGL you can use these shader code to draw something and then clear it up with use program 0, right? So that's what I was talking about just a minute ago. It's the same thing, right? Okay, so this is the actual code Yeah, you have to write a program to read a file, this one and this one, and these are with the GL is already inbuilt, so you don't have to worry about these. But obviously read file, I had to figure out the way to read these things in. Okay, right. Right, so debugging part. So yeah, when you're talking about the debugging on this, you don't have much flexibility these days. You have actually the Visual Studio. If you're using CUDA, Visual Studio has its own way of debugging things, so that helps, right? And early days you did not have it, so it is really hard. No printf or anything that you cannot have in the shader code to print out the variables or things like that and look at visually what is the value stored in there, right? And so still if you don't use CUDA or if you're using something else, debugging is very hard to do, right? And but if you want to have the shader error and where is the problem and all that, you can get those data with Infolog actually. So we did this part in our lab and see where the problem is. If you have some problems to get information out, you can, right? So that debugging part is there, very simple straightforward debugging on the logic errors mostly, like if you put for example if I have a float a, if I set a equal 5, this is not going to work, right? So you have to have a equal 5.0, this is works, right? So those kind of things are there that you have to worry about when you're writing a shader code, especially in GLSL. So yeah, these kind of errors will point out by Infolog, right? But not most of it. So you don't know, you cannot look what is inside the AI actually by visualizing it by any debugger technique. Like I said, in CUDA you can, but not in mostly shader coding like a GLSL. It will be hard, right? Okay. Right. So the variables again. We have uniform is the first variable type. I already gone through this one, so I will address this very briefly. These are actually handling by the CPU side, and you can pass the data, but passing the data from outside of GL begin and GL end, keep that in mind. So if I want to pass some values from my shader code to the GPU side, I can using the name uniform, and it is not for per vertex, it will be the whole thing. For example, I'll show you example on the next lecture. Actually we will look at this one a little bit more beyond this level, right? And attribute on a vertex, the per vertex basics, that is we call attributes and uniform. So there are some other varying and all that, so we'll look at these things as a complete example on the next slides. I mean the next lecture I'm going to combine to this anyway. So we'll look into these things into more depth, right? So that's what we're going to do next. So this is the next lecture, and I'm continuing from where I left off, where we're looking at actually looking at the shader code part. I'm the shader side of the program now, and how the shader coding is related, right? And so we're looking at the vertex shader right here. So there are some keywords that you have to know that I was discussed that in the previous lecture as well, related to shader coding right here as well. So you can see here, these are the keywords. Actually G underscore whatever you have, that is a keyword. In this case I'm taking care of the vertex, so it is a per vertex at a time that it's handling on this code. That means each vertex will distribute into parallel the units in the GPU and have. So here you may notice that you have vector 4, right? So this is vector 4. What is vector 4 means? Well, usually you have x, y, z and w, right? So this is what vector 4 means, right? Remember, this w is coming when you want to get it as a 4 by 4 matrix. So we introduce something called homogeneous coordinate system, which is this one right here, right? And the rest is x, y and z, and then whatever you have there as values, right? So in this case, if you want to multiply this by x, y and z, obviously you need something else as well. So that is the w part which is coming into play. This w will make it scalar value. So if it is more than, if the w is 1, it will be the same size. If it is w is 2, that means it will be big like this, right? So anyway, so vertex, this gl underscore means that you have the keywords from the vertex shader, right? So that's how you define the keywords, right? So then the vertex is passing a vertex here, right? So it's a per vertex operation. So that means if I have here x, y, z and x, y, z 1, 1, 1, x2, y2, z2, right? In this case, one vertex at a time it will be operate actually. So this operation apply for one vertex and then it move to the other, right? So here what I'm doing is I'm taking it as a the vector 4. This is local for this function, right? And then what I'm doing is I'm applying the x value of that and then the y value of that, right? So only these two values of vector 4, right? And then I multiply it by 0.5. So it's getting it's scaled, right? So it will be scaled to some size, right? So that's what I'm doing here, right? And then the position means the what I'm returning here. So the position is the one which is returning by the vertex shader most of the time, and the position will decide by the model view projection matrix multiplied by this value. Okay, so there's another way of writing this, of course. GL positions, either you write it like this or you can say that the F transform, that is also works, right? And so these are the ways that you usually display this. This is a much better way of doing that, because this matrix right here is a construction of model, view and the projection. So it will be having all the values right properly, and then you multiply that by your xyz coordinates. That will give you the exact final position of it. Okay, so this is actually the very basic program which is changing the scale of the position. So you take it, this is the input right here, and you do whatever the operations you do, and this is the output right here. So this is the input, right, and then this is the output. Okay, so that is the very basic idea of it. So yeah, so let's look at a little bit further on this, so we can see much what is this actually did. Well, that is the scale by 0.5. I think the 0.5 scaling means you're just scaling down. I think this diagram has a little bit wrong information in that case. If you have the value and then if you multiply by 0.5 means actually you're dividing by 2. So in this case, if I have the object, if it is according to the previous calculation, this has to be smaller than this, right? Okay. But anyway, then what you do is a fragment shader here, and the fragment shader is changing the colors. So I have this color is white, and again converting everything to the vector 4, and in vector 4 what I'm going to do is I'm passing these colors right here, right? So it is 1 0 1 0 1. So this is the alpha value right here at the bottom. So what are these factors here? Well, this is alpha value, right? So this is alpha. Alpha value means the transparency, and this is red, this is green, this is blue, right? So I have blue 0, red 0, and then the alpha is 1, that means there's no transparency, and the green is up. So that's why you're getting this kind of color here. Right. So that is the way the fragment shader is taking care of lighting. Whereas this is a very fundamental, simple program, right? And then if we move further on it, if I want to see the passing values from the outside to the inside, so where are you going to store those values, right? So here at the passing values to the vertex shader, we're using a variables called uniform variables. So the uniform variables actually communicating with the CPU side of the program. Like for example, if I want to pass the scale values, I want to pass the scale from my computer, right? And in that case, you can use the outside program. So the uniform variables are read only, and it's the same value it will be for the everything. If you are using one value, it will be the same for all, right? All the vertices you're passing in, it will read the same value. You can only change those values in the C program side, so that means the CPU values you can pass it from there. So this is the example of it. Uniform float, you can define it as my variable. So that's how you're writing it anyway. So that's what it's showing there. How do you write that in terms of the shader coding? So this is how it rewrite it. So you just put uniform in the front of float my variable, right? Okay, so then this is the example of it. So you may notice that we have defined it globally right here, right? So this is the global uniform scale variable, and then I'm taking again one of these corners, right, and one of them. So I'm taking that value and multiply by the scale. So in this case, I had to pass the scale to this guy from the CPU side. Otherwise, it won't work, right? So how do you do that? Well, first you have to find the scale, right? So in the CPU. So this is where the CPU part comes in. So when you're writing the code, you say, okay, I want to get the location. And then when I get the location, this is how you get the location. And then this is the program. Actually, this is, remember that we talk about encapsulating, saying something GL create program, right? Program, right? So yeah, something like that. And then I can give the name. So that's the part right here, right? So this is the part right here, and I say okay, so find the name scale. So once you have all these read into this little thing as a one program, right? Remember that we did that already with the compilation of these two, and then we store it here, right? This is your vertex shader, this is your fragment shader, that we create the shader, and at the end you just compile the shader, right? So this is compiling the shader and then put it in there, and then whatever you do here, it will be take care of those values from this object which is I created, right? So and then it's looking for the scalar. So if you find the scale value in there, you say the GL uniform location. So this is where this is location, and you set the value in there. See, assign number 4, right? So in case if you type just 4 instead of 4.0, this program won't work, right? So the reason for that is I just already called this a float. So those are very simple things that people can do wrong. and you're never going to find it if I put just 4 here, right? So that's the incompatibility of the passing values. So you have to define actually in the float form if you're putting a number there, right? So this is how you pass that value. So when you pass that value to this function, actually your triangle become 4 times bigger. So that's actually what's going to happen here, right? All right, so I think that is straightforward, and you can pass the values like this for anything like that, right? Right, so this is assigning built-in variables. Usually in the vertex attributes, we have few of built-in functions that you will see, and you can address these. The one is the vertex, GL vertex, that has a position of 4. And you have a GL normal, which is actually, if I have this, we have to calculate that one value. Or you can pass that value straight after calculating, whatever you want to do. And then the colors, of course, so this one also have X, Y, Z, and W, right? Usually W is 1 in this case, right? And then the GL color also, we have R, G, B, and then the alpha value. So this is also vector 4, right? And the texture coordinates actually using only if you basically using only 2, but you can extend that up to 4, but the other 2 has no meaning in it, right? So you can put anything you want. So I can just handle only the X and Y in there. Okay, so this is a multi texture code. That means all the texture codes, if you want to pass into the system, using this too, right? How do I identify my color? Well, if you're having a triangle like this, usually the vertex, you say GL vertex 3F, so they can pick that. If you have a GL color 3F, they will pick this, right? So anything else that you want to do this, you can. Otherwise, it will pass the whole thing as a VBO or whatever your preferred way of doing that. So this is what it's handling, right? And this is where it's picking up all this data, right? Okay, right. So that is just a the way of things. I mean the keywords defined in the vertex attribute, right? Right. So then the communication through varying variables. So the varying variables, I already talked about this just a while ago. This is how you communicate in between shader code. So we have vertex shader and the fragment shader. So we have to communicate those two guys. So if you want to pass data from one to the other, we're using a variable called varying. But the only thing that you have to concern here is this shader code is runs before this guy. Okay, so that means after you execute this one, if I have to update anything, I don't think it has so much connection to reverse or the other way. So in that way, varying color, whatever the varying color is taking here as a GL underscore color, and that will take care of the color part, and then you can pass that directly to the fragment shader, right? So that is one thing that you can do actually. Anyway, whatever you do here, the output part is always handling by the fragment shader. There's no way that you can output or the showing something in your vertex shader for the colors related. So you cannot paint anything using a vertex shader. You have to have a fragment shader in order to paint anything, right? So this simple example is varying a color means I'm taking the color from CPU side, right? I mean, I'm sorry. The varying a color means you just passing this one from vertex side to the fragment side, right? In this case, I'm taking the values from GPU directly. I mean, wherever it's picking up from your VBOs and PBOs and stuff like that, and then it's pass it to vColor, and then vColor passing to here. So that's what this process is, right? So this is an example of it. It's pretty neat example. You can test it if you want with the lab code that I have already done. So this is varying. I'm passing my x value, I'm passing my y value, and I'm passing my z value, all three together. I'm passing here from here to the fragment code actually, right? And then I'm taking the positions of it. So then I'm fine tuning the positions by clamping it with these values here, right? The clamp means you get exact value from whatever you using x, y, z, and all that. And then of course I'm displaying it with the GL vertex. But here I'm going to use these values just for the paint. So in the color part, I'm assigning these values. So this is what you get when you do that. This is the color value, color cube that you get, right? So this is how you just do it in the shader aspect. How do you do the color cube, right? Okay, so that is very neat program that if you want to look at it, you can play around with it and do and see. So now this is a color, playing around colors, right? So we can do the playing around with textures as well. I'm not sure whether I complete that project in the lab, that we give a new texture and then color it with a different color. I'm not recalling that I did that for the undergrads maybe. The grads classes maybe, but I did not. I'm not sure. But let me know if you really interested in changing color of texture. We can introduce that in the lab if I miss it. Right. So usually the textures contains images data, right? And then the GLSL texture is specified as uniform variables, right? So these are uniform variables actually, texture data. So that means, yeah, you can take these from your CPU side, right? And then it will be same for the whole the process of the shader part. So that's why if you're using as a uniform, right? So it's considered as a uniform. And so yeah, it has RGBA, right, usually. And so sample, usually you're using sample 2D, right? That is the array you kind of using. Let's look at the example. How do you pass this data and what you're going to do with it? How do you change these colors? Right, so here it is. So what I'm going to do is change the texture color, right? So first thing you want to do is passing my texture code from my shader, vertex shader, to the fragment shader. I do that there, and whatever I have for the current object that I'm handling there, the texture code for that will be on multi-texture code 0 in this case, right? So I'm just having that, take that value for texture code, and obviously I don't have anything to do with the position, so the position will be the same. And I'm going to move that guy, move that color into my vertex shader. So what is, the fragment shader. So what is the fragment shader look like? So the fragment shader taking this value, right? So that is one thing, and it's also picking the values, picking the image. This is the pixel pack. We call it my texture. So I'm just having a sample 2D value of the image. So I'm taking the values from my the CPU. This is the image data that I'm taking here. So sampler 2D, my texture is that. So when I say the sampler 2D, it will bring all the RGB pack values to my texture code. And then actually XY values I'm passing from my vertex shader to the fragment shader right here. And then I will have, now this is the original color I have, and this is the codes that I'm using from my the vertex shader, and it will be the same code that I have given to the vertices, like, by the GL texture code, right? So that is where this texture code comes in. in the GL begin and GL end, in between we have a texture code, right? So that's what it is, right? And then here I'm taking the RGB value. So usually when you're having something like this, usually you have R value, G value, and a B value, and the alpha, right? So I'm switching it here. So in that case, whatever I have as R now will be the B. So if I have some picture like this, for example, let's say I have a picture like this, and this is my R's, so it is a red color, and that is my red part of my program, right? So this is what it is, used to be, right? It's a red color, right? And then I have the green. So this is my green color of my image, right? And then I have some blue color here, right? This is a blue color, right? So this is RGB. And when I say, okay, shift those values by BGR. So what happened here is, instead of I'm getting red here, I will have the blue box right here. So if your original image is having red, now it will be updated to the blue. Green will be the same, and then I'm going to take my the blue one, I'm shifting that to the R. So this part right here will be R, right? So that's the difference from the original image. I'm switching the values. So this is how it's going to be look like at the end, right? So this is how if you want to play around with textures, these are the most simple basic examples I just gave you here, and you can go to the depth and do some crazy stuff. Actually, I mean, pretty cool stuff using these concepts, right? So I will stop here talking about shader coding. Actually, in 90% of these 2 lectures we did already practically on the lab, so that's why I'm not going to pushing it much. So okay, so what left, actually we had to talk about WebGL and then GPU programming, but I want to do 2 more labs related to the animation and related to the assignment I gave you. So it will be 3 labs I'm going to post within this week probably. So those are important ones, so you can go through that anytime you want, right, leisurely. Yeah, so okay, so I'll see you in the next lecture.